Okay, so today we're doing equilibrium graphs. Now, our syllabus outcome for this is investigate the effects of temperature, concentration, volume, and/or pressure on a system at equilibrium, and explain how Le Chatelier's principle can be used to predict such effects. For example, heating cobalt chloride, interaction between NO2 and N2O4, iron thiocyanate, and varying concentration of ions. So this is the equilibrium graphs is more of a visual way of looking at Le Chatelier's principle. Okay, so here's the answers for the revision questions. Again, we're just going over that Le Chatelier's principle. If an equilibrium system is disturbed, the system will move to minimize the change. Okay, if we add something, let's say we add a product, it will shift away from that side, so it will shift towards the reactants. If we increase the pressure, it wants to decrease the pressure, so it will move to the side with fewer moles. And if we increase the temperature, it's going to want to decrease the temperature. And so it'll move towards the endothermic side, so the side that lowers the temperature. And all of these things, they work both ways. So, if we take a chemical away, it'll move towards that side. So, if we take away reactants, it'll move towards reactants, etc., etc. Hopefully by this point you've got that all sorted. Um, as for our equilibrium graph, so this is often depicted using a concentration versus time graph. So we have time on the x-axis, concentration of all of our products and reactants on the y-axis. These equilibrium graphs, they're a visual way of following the behaviors of chemical species in our equilibrium systems. Firstly, when we put reactants into a reaction vessel and close it off, because remember we need a closed system, we allow it to come to equilibrium. So what this will look like is, we start with a high concentration of reactants, no concentration of products, and they slowly come to a point where they're at constant concentration. The change is rapid at first because the difference in reaction rates is quite stark, but as it tends towards that equilibrium, the difference in the reaction rate slows, like it becomes closer, and so the reactions slow, and eventually we get to that point of constant concentration. And remember, at equilibrium, the rate of the forward and reverse reactions are the same, so the concentrations of the reactions stay steady. So this is what one looks like. This is just a basic one where we've put in some blue reactants and they've transformed into some red products. Now we can see that at first it's quite stark, it drops off fairly quickly, but then the reaction rate slows to a point where we reach equilibrium, and then the reactions are steady. The concentrations are steady. Now it doesn't have to just look like that, it can look like that as well. We can get, it depends on the reaction, but some will favor products, some will favor reactants, some will be about equal. Okay, but we can still see that same motif where the reactants react quickly at first, slow off to a point where the gradient becomes zero. So when that happens, we've reached equilibrium. And on the opposite side, because our reactants are going down, our products are going up. And again, it reaches a point where that concentration doesn't change. That's our point of equilibrium. So the different changes to the equilibrium that we can look at on a graph. If we disturb the system, the equilibrium system, it can be shown on these equilibrium graphs. Now, different disturbances cause different characteristic changes in the graph. For starters, adding a single reagent. So this is going to be adding a product or adding a reactant. Basically what happens is when we do that, the concentration suddenly increases. Now we normally do it, so as if it's instantaneous. So it'll happen, over zero time. And then the equilibrium then moves to counteract that increase. Now, so what does this look like? So this is what it looks like in an equilibrium graph. You can see here our reaction is A is in equilibrium with B plus C. Okay, and so we're going along at the start, everything's at equilibrium already. It's got that constant concentration, and suddenly at that time point, the concentration of A jumps up. So what's happened here? Well, we've added a whole bunch of A. The equilibrium will then move to minimize that change. Okay. And so what happens? A starts to, that means it's moving towards the product side, which means B and C are being produced. Okay, so we're using up A to produce more B and C. When we remove a single reagent, so again, it could be removing a reactant or removing a product, it's almost the same as what we were just doing, except that the concentration suddenly decreases. So it's the concentration of just one of the reactants or products. The equilibrium then moves to minimize the decrease. So what does this look like? Well, let's assume we've got this equilibrium system. So we're using the same equation. A is in equilibrium with B and C. Uh, Everything's at equilibrium. They're all constant concentrations. And then at a certain time, we remove a bunch of A. And so the concentration rapidly drops. We can see then that the equilibrium moves to minimize the change by producing more A plus. And as we're producing more A plus, we have to use B and C to do that. Okay, so we can see the concentrations in B and C are dropping. Now, increasing the pressure, what does this look like? Well, when the pressure inside the reaction vessels increase, the concentrations of all the reagents will increase. So that's both products and reactants. The equilibrium system will then move to the side of the reaction that has fewer moles, as the fewer number of moles reduces the pressure. And so remember, that's an offshoot of Avogadro's law, where number of moles is in proportional to pressure. And pressure can only be changed in gaseous reactions. So we can't really change the pressure of our aqueous stuff. Okay, it doesn't really affect it. It's more for gaseous reactions. What does that look like? Okay, so here we've got, again, we're going to be using the same reaction. A is in equilibrium with B and C. Everything's at equilibrium, and then we go along, and at a certain time point, all of the concentrations jump up. Okay, so basically what we've gone and done is suddenly increase the pressure. Okay, so remember, if we increase the pressure, we're increasing the concentration of everything in the vessel. So you see it's all gone up. Now, if we have a look at the reaction, A is in equilibrium with B and C. There's 1 mole on the left, 2 moles on the right. And so it's going to go towards the side with the fewer moles, which will be A. Okay, so you can see that A jumps up and then the equilibrium starts to make more A. But we can see with B and C, the equilibrium jumps up and then moves to take away B and C. Now, decreasing the pressure, again, almost the same as increasing, just in the opposite direction. So when the pressure inside the reaction vessels decrease, the concentrations of all the reagents will decrease, so both the products and the reactants. And the equilibrium will then move to the side that has the larger number of moles. So having a look at this on a graph, we can see that again, everything's at equilibrium. At a certain time point, the pressure in everything just suddenly drops. Okay, so we've reduced the pressure, we've increased the volume. Now, having a look at our reaction equation, when we reduce the pressure, it's going to want to counteract the change by increasing the pressure. To do that, it's going to move to the product side. And so we can see that the concentrations of B and C increase after that change, and the concentration of A reduces after that change. Now, change in temperature. So when the temperatures change, the equilibrium will shift to minimize the change. This we know. The way the equilibrium shifts depends on the enthalpy of the reaction and whether the temperature is increased or decreased. So this appears as products and reactants reaching a new equilibrium on a graph without any sudden changes. Okay, so what this looks like on a graph is just like this. So we can see all the concentrations are at a steady state. Time point happens, and then we just start to get that equilibrium change. Okay, there's no sudden jump up, jump down of any of them. It's just that new equilibrium coming to form. Now, we'll do some questions later, but basically, when these questions pop up, you will be given the enthalpy. You might have to guess the temperature change, or If you're given the temperature change, you might have to work out the enthalpy qualitatively, that sort of thing. So we're not going to go into too much detail here, but in the actual questions, you'll be able to figure out what's going on. So here's just a graph I made. What I want you guys to do is to pause this video and figure out what's happening at time points A, B, C, D, and E. Are we having an increase in pressure, a decrease in pressure, adding a reactant or product, removing a reactant or product? Or now, because I haven't given you a reaction, you don't have to tell me what type of change in temperature, just tell me if there is one. Okay, so pause the video and do that, then we'll go through the answers. Okay, so here are the answers. The changes. The first one is a removal of compound 1. So you can see that the concentration of compound 1 suddenly drops at time point 1. After that, the equilibrium moves to minimize the change by making more compound 1. At B, it's an increase in pressure, so we can see all of the concentrations of all of the reactants and products spike up, and then slowly come to their new equilibrium to minimize the change. C was a change in temperature, so we could see that there was no sudden changes at all. Okay, and that just shows that it's a change in temperature. D was the addition of compound 2, so compound 2, the concentration suddenly shot up, and then the equilibrium moved to minimize the change by getting rid of compound 2, so reacting it to form the other compound. And E was a decrease in pressure, so we saw the concentration of all of the reactants and products decrease suddenly. Now, there is a bit of quantitation in equilibrium graphs. Most of it is qualitative, so we could say, okay, which way is it going to go, and we can draw it out a little bit. But there is a bit of quantitation that can be important for some HSC questions. And the part that is quantitative is generally to do with the molar ratios. Now, what do I mean by that? Basically, when the reaction shifts towards one side, the reactants react in the specific stoichiometric ratios according to the reaction equation. These ratios are then reflected in the graph. Now, here's an example. The good old Haber process, we have nitrogen plus hydrogen giving us ammonia. Now, I can see at that time point, we've removed a bunch of ammonia. The equilibrium shifted to minimize the change by producing more ammonia. Now, the amount of that graph goes up on this graph is 2. And we can see that as that's produced, so those 2 moles of NH3 are produced, we remove 1 mole of nitrogen and 3 moles of hydrogen. Okay, so it's in that ratio. So NH3 goes up by 2, N2 goes down by 1, H2 goes down by 3. Okay. So yeah, our 2 equivalents of ammonia are produced, while 1 equivalent of nitrogen is lost, 3 equivalents of hydrogen are lost. Here's another example. We've got 2 SO2 plus O2 in equilibrium with 2 SO3. So you can see our SO3 concentration increases by 4 squares. Okay, I haven't actually put any numbers in this, but we'll just use squares for now. So SO3 has gone up by 4 squares. If we have a look at the stoichiometric ratios, we should see an equivalent decrease in SO2 because they're 2 to 2, so 1 to 1. So the same amount of SO2 is removed from the system as is added to it. Now with O2, O2 has a stoichiometric ratio of 1. And so it's going to be half the amount of change that SO3 or SO2 will have. Where SO3 and SO2 change by 4, so O2 just changes by 2 squares in this example. And it's going down. So because we've changed the temperature in such a way that our SO3 increases. For SO3 to increase, it needs to get made by reacting SO2 with O2, so those decrease. Okay. So here, what I want you guys to do is to use that quantitation method and see if you can figure out which one of A, B, and C is those reagents. So there's going to be 3 chlorines plus 2 phosphoruses are in equilibrium with 2 phosphorus trichlorides. Now, what I want you to do as well is to justify your answer. Okay, I know we haven't done much on the justify verb, but you basically have to put in reasons for your decisions. Okay, don't just say A is this, B is this, C is this. You need to tell me your reasoning. So pause the video, have a go at that, and we'll go on with the answers in just a sec. Okay, so our answers. Let's have a look. If we have a look carefully, we can see one of the reactants is going up and there's 2 going down. Now, if we look at our reaction, there's 1 product, 2 reactants. So it stands to reason that A is PCl3. Okay. Yes, the concentrations of B and C go up, goes down, A goes up. There's 1 product, 2 reactants, so A is PCl3. Now, out of B and C, which one's which? Which one's the 3 Cl2s, which one's the 2 phosphoruses? Well, this is where our stoichiometric ratios come in. We can see that for every 2 moles of phosphorus trichloride that we make, we use up 2 moles of phosphorus and 3 moles of chlorine. And so B goes down by 3, C goes down by 2. So B should be Cl2, C should be phosphorus. Okay, so in summary, changes in equilibrium systems can be shown on concentration time graphs. Different disturbances result in different characteristic changes. So remember, adding a reactant or product spikes that one particular product up or down. Change in pressure spikes all of them up or down. Change in temperature has no spike at all. We just get a smooth change towards a new equilibrium. Now, and don't forget the quantitation, so changes to the equilibrium system will happen in stoichiometric ratios. And that is all for today. Thank you.